Okay, so thanks very much for the introduction, for the opportunity to talk here, and thank you so much, Shay, for the great talk. I think there could be no better motivation for the talk that I'm going to give now. So I'm going to talk about a project that I did at Environment and Climate Change Canada with my co-authors listed there. Let me just jump into the content. I'm going to have 4 different parts. The first 2 are really short and introductory. So first of all, because I'm talking about air quality, which is maybe not so known to some of you, I'm going to give you a little bit insight about what specific challenges we have in air quality data assimilation, and then give you a very short introduction to the parametric Kalman filter. This name was already mentioned by Shay before, so it's going to be very short. And then I'm going to go into my work and show you a little bit about the theoretical developments that I did, and then the case study application for wildfire smoke event in Canada. So jumping to the first part, why is air quality data assimilation and modeling so challenging? So of course, we have modeling challenges or forecasting challenges and data assimilation challenges. And on the one side, we do have research challenges. The first thing, air quality, we have a lot of species, so prognostic variables that are interacting. So you can have up to hundreds of different chemical species. So we have a large model space, and usually most of the variables are not observed or very rarely observed. So the model space is really much larger than the observation space. And we also do have some cross-species correlations, which I'm not going to consider this talk at all. And also for air quality, this is really determined by very uncertain emissions. So it's not so much about the initial state that we care about, or that determines our uncertainties in the systems, but it's really about emissions and other processes coming through the prognostic development. And since they are so uncertain, we have highly to rely on the observations, and we expect large corrections due to the observations in our assimilation system. And this is particularly true if we think about extreme events. And there is where wildfire is a very nice example, I think. And I put a little picture here from a wildfire in 2023 in Canada, which will also be my case study later on. These extreme events are very case specific. So every fire, every extreme event is different. And of course, not only the state is different, but also the errors are very different. They're non-statistical, they're very case specific. And also, since it covers a lot of range, a lot of scales, and also not only the state is spatial temporary, very variable, and we have a lot of gradients, also the errors are. So the errors and the uncertainty correlations are highly variable, non-uniform, and anisotropic. So we can summarize that these extreme events are very uncertain and have exceptionally high impacts and complex uncertainties that we have to deal with. On the other hand side, we do have operational limitations and challenges, particularly also for these extreme events, but also in other air quality problems. One thing is that we have this high public interest and really a need for real-time updates, which is particularly true because fires cannot be predicted themselves. So we have to wait until a fire comes up, and then we can start detecting the fire, for example, with satellites, and really have to wait on this real-time input to get any kind of chance to estimate our emissions. So the system that, of course, should be fast and efficient, but still accurate to provide the operational needs for the public. So this motivates, in general, trying to use a parametric Kalman filter for these kind of applications. Just to give you a rough idea what the parametric Kalman filter is. So just think about key error parameters of your uncertainty distribution that you have from the state. So a very simple example is given here. So it's just a Gaussian probability density function. And instead of having an ensemble with different realizations indicated by the green bars, you could easily define the uncertainty given by the error standard deviation in this case. So this would be one of the key error parameters. If you go to higher orders, and this was also mentioned by Shay before, you can think about the error correlations. And this could be the length scale in one dimension, which is shown here, for example. So if you have the space indication, of course, you can define your two-dimensional covariance distribution by a variance and a correlation length, but you could even think about higher order terms. Just before I go on, I would like to give you a very short one-dimensional example. So on the x-axis, you have a space index for a very just artificial test environment. And then I'm showing the error variance field. And this dotted line up here, which is a little bit randomly correlated, but these are the background error variances that have been generated. And then I also introduce an observation, which is located here. So the location indicates the observation error variance at this location. And then, of course, if we do the assimilation step, we get an analysis variance, which is lower than each of the observation and the background variance, this is just a little reminder for you because it looks different when we think about the state as we think about the error variance. And then when we have the analysis, of course, we would think about the propagation of the errors. And then if we think about explicitly propagating, for example, the error variance or the error standard deviation in our prognostic model, which is in my case, the atmospheric air quality model. And here in this case, it's just very simple diffusion. So you have the error variance of the analysis, and then you apply very strong diffusion, and you can see that after the diffusion, the error variance is significantly lower and smooth. And I'm going to go back to this later and explain a little bit why and how that works. But first of all, I'm going to give you a very short comparison of the parametric Kalman filter in contrast to other Kalman filters that you all know. So original Kalman filter or full Kalman filter, you also heard about this before, would involve the full error covariances. And we all know that for high dimensional applications, it's just not feasible to implement and even to store the high dimensional covariances. And even if we would be able to, the initial error covariances are just not known in detail. So we don't have the knowledge to fill these high dimensional matrices. So that's why very successfully the ensemble Kalman filter is applied in a lot of different variations and a lot of different applications as well. It has been shown to be feasible for large and complex systems, but it also comes with some limitations. One of them you heard before in the last talk, related to the not only to sampling errors, but also to the discrete propagation of errors. One other main disadvantage that was the motivation for my work is that you have to have many forecast model executions to have a suitable error estimation, which is often not feasible, especially if you have limited computational resources and operation. So to put this in a comparison, the parametric Kalman filter comes with very low computational cost, because if you imagine you just do one forecast run, but you have additional variables in your system that represent the key parameters of your uncertainty distribution. So for example, the error standard deviation, which is in my case. If you do that, you also have to, of course, you have to derive the prognostic equation. How do my error parameters evolve over time to be able to implement this into your model, which can be a disadvantage. And this can get very complex, especially if you increase the number of processes and variables that you consider. At the other hand side, you do have this explicit equation, and you can really understand the dynamics of your errors in your dynamical model, which I think is a great advantage of this method, and very interesting as well. So now stepping back to my concrete work and the theoretical part first. So I was looking into a very simple parametric Kalman filter focusing on the forecast step. So I'm not doing any focusing on any analysis step, just the forecast in an operational air quality model by adding an additional tracer to the model, which represents the concentration error standard deviation of one tracer that I'm going to tell you about later. But if we think about adding a new tracer to the system, of course, we always need initial and boundary conditions. In this case, if we think about the error standard deviation as the tracer, you have to implement this somehow. And I use a very, very simple approach, which is based on the currently operational data assimilation system, where a statistical correlation, a statistical connection is drawn between the background concentrations and the background variances at each location. So there's this very simple slope that you see here, a linear correlation. This is used, and because I'm using error standard deviation, I just take the square root of that to get my initial and boundary conditions for my error standard deviation. And then we already talked about emissions are super important. So basically emissions are a source term of concentration, as you see here. So this would be a state concentration and the change due to emissions, which are on the right-hand side, are given here. So because emissions are very uncertain, they are also a significant source of uncertainty in the air quality forecast. So it should also be a source term in your error variance or error standard deviation form. And this you can actually easily derive by using this equation and then applying the definition of your error standard deviation to this equation. And if you do this, you end up with a very simple equation for the error standard deviation. The change of error standard deviation is just given by the emission error standard deviation, which you have to define again. This has also been implemented now. And I also use a very, very simple linear relationship using the same slope now between the state emissions that are giving to the source term of error variance. And this linear relationship using the same slope as for initial and boundary conditions ensures that we have a consistent impact on the state. So it does not matter theoretically if the emissions were emitted before I start my simulation or within my simulation. The impact on the uncertainty forecast should be the same. And that's why I use this very simple approach. And again, from this linear relationship, I take the square root relation to get the standard deviation. Once we have this, we have the dynamical propagation, of course. And what I'm considering here is a three-dimensional advection. You also saw this before. We just take the advection equation for my state concentration, and using again the definition of error standard deviation, you can derive the equation for the change of your error standard deviation due to advection, and it appears to be exactly the same form, which is very nice because that means you can just use the same advection scheme that you already have in your system for your other traces and just let the error standard deviation be advected exactly the same. And it also makes sense if you think about it. The picture looks different if we go to diffusion, and I just have one-dimensional vertical diffusion here, but conceptually it works the same even for three-dimensional diffusion. If we start again with the diffusion equation, we end up with a different equation, and I put here the change for error standard deviation and also for error variance, because what's quite interesting here that both equations have additional terms, but they are different. Although mathematically they're exactly equivalent. And also a note, they now include the vertical error correlation length, which is not considered in this system. So I just do a very simple assumption there, but it's not propagated in the system. So looking a little bit more into detail about the two equations. The two blue parts are exactly, again, the diffusion equation of our model. So again, we can use the diffusion scheme in our model, but then we have these additional terms. And in the equation for standard deviation, then we have this green term, which is also very similar to this green term I tried to sketch here for the variance. But for the variance equation, we do get a third term, and this even includes another spatial derivative of your variance. So it gets computationally much more expensive. You get additional numerical errors because of the discretization. And it's also more complicated to implement because this green part over here is just an additive term that you can easily implement into your system. Coming back to this one-dimensional example that I showed you before, so I hope you remember the plot, and now thinking about the step from the analysis variance field, error variance field to the forecast by just applying very strong diffusion. And I'm going to show these are the contributions, so the changes, specifically these different terms with the same color code, how each of the terms changes the error variance or the error standard deviation field for the first time step that I'm considering. So this is for the error standard deviation form, and this is for the error variance form. You can see the blue lines. They are basically just this moving that we know from diffusion. So if the variance, where the variance field was low before, like here, it increases, and the other way around. The second term is always negative, and it actually appears that this term is just the fact that if we have some kind of noisy signal, so uncorrelated errors or random errors in the system, and if we apply diffusion, then we would always assume that these errors disappear. So the green term is just the fact that if we have uncorrelated or noisy errors, we expect the error standard deviation or the error variance to reduce. And this is what you see here. It's always negative. The third term is much more complicated to interpret because it's kind of a geometric term that only occurs in the variance field. Again, mathematically, the two are exactly the same. Due to the additional term, numerically, the standard deviation term appears to be much more accurate. It's easier to implement and also easier to interpret because you have these very clear two terms with two different processes going. Okay, finally going to my case study application. So I'm looking at a wildfire smoke event in Eastern Canada, and I implemented this forecast equation and the setup that I just explained to you in the coupled air quality meteorological model, GEMMEC, which is the operational model at Environment Climate Change Canada in its regional operational setup, which also includes a special module for near real-time wildfire emissions. Since we are really relying on the latest updates, it's really important to have this component in there. And I'm looking at total fine aerosol concentrations, which is always indicated as PM2.5. So this is the case study. It's from Eastern Canada, so I'm always going to show a little subsection of the plot with showing the Hudson Bay here. This is Montreal, Quebec City, Toronto, and New York City would be somewhere down here. So we're in Eastern Canada in the beginning of June 2023, which were very large wildfires. And you can see from this background concentration at one time, the large fires with this large emission sources up here. And you can also see that they were directly transported southwards towards the main cities, which had significantly increased air quality issues. So I implemented this additional tracer, which represents the PM2.5 error standard deviation into the model. And I'm going to only show you results from hourly surface analysis. So up to now, there's no feedback to the next hour forecast in the system. So no full assimilation cycle, just an offline hourly analysis. And I'm going to compare my results to the currently operational assimilation setup. So I'm showing 4 different hours that you can see from left to right. The upper row is the background state that you already saw before for 1 hour. And please note that this is a logarithmic scale in concentration, so you can see how it is behaved, and you can see the strong signal from the fires. The lower 2 rows are the background error standard deviations, first from the operational setup and then from this new parametric setup as predicted by the model. And the first thing that really comes to mind is that the uncertainties with the parametric setup are considerably higher. So we're really talking about orders of magnitude because this scale is also logarithmic. And it's very flow dependent. So you can really see, if you compare with the fire plumes in the top, you can really see the shape of the fire plumes being attributed to high, high uncertainties in the system. But we also do see some considerable differences. For example, in the southern region, because we're not including area emissions and other processes, but we're really focusing on the fire plumes. And disproportionality is just because we don't have any feedback. If we would have an analysis feeding back into the next forecast, the picture would look quite different very fast. If we then assimilate surface observations that are indicated with white dots at each of the plots, then I'm going to show you on the left side the operational setup, on the right-hand side the parametric setup for 1 hour. You can see that in the southern part of the domain, where we have a lot of observations, and these are the urban areas, the increments look quite similar in both setups. But the more far away we go from the observations, then we can see considerably differences. Particularly, we can see also in the increments clearly the different fire plumes, and that the strong concentration, the strong increments that are indicated from observations quite far away are largest at the plumes. And I just want to note that this large spreading of observation to very remote areas is not because we would change the error correlations. The error correlations are exactly the same in both setups. It's just because the error standard deviations, so the variances at these locations, are so large that even with a very low correlation, we get large increments attributed to these systems. So lastly, just showing you also the evolution for 4 different hours. Again, this is the same arrangement as before. We have here the operational increments and here the parametric increments. And what you can really see is that we have a large spatial, but also temporal variations. The increments often change sign even within 1 or 2 hours. So we really have a large variability that we have to capture. And what you can also see in certain regions, if we have observations that are indicating opposite directions of the increments, this can be represented by the system. Whereas if we don't have observations indicating opposite, or if the observations are pointing towards the same direction, like at 9 UTC, we get a common signal along the plumes, which is really consistent. But if the observations don't agree, then it's able to even induce different signs of increments in the model. So coming to my conclusion, I've been talking about the parametric Kalman filter and particularly an application in an operational system. This is really an approach which has advantages but also disadvantages, but we do think that it's a very nice alternative to for high dimensional systems because it's very computationally efficient and it has a lot of advantages that you can make use if you're interested in this. And one advantage that I really want to point out is that you get explicit information of the dynamics of your error field in the model. And in this regard, it turns out that the error standard deviations seem to be more suitable than error variance if we think about the implementation into an operational model. And finally, it's able to create very case-dependent and flow-dependent error estimates and also increments, which are particularly aligned along the fire plumes in my case study. So this indicates that we might have improved use of very sparse observation networks because we are representing the errors in a very flow-dependent manner. So that's all what I have. Thank you a lot for your attention, and I'm very happy to take any questions. If you have further interest, there's a paper about all this in discussion at NPG. Thank you.
Thank you, Annika. That was a very fascinating talk. Looks like we have 2 somewhat related questions in the YoPad. So I guess I'll state them as one question. First, are error correlations across space and between species also being propagated through the dynamics in your method? And if they're not, then we have a question from Shay Gilpin, which is she's wondering how you would evolve these correlation length scales and implement the evolution in your system.
Yeah, that's a great question. So in my application up to now, they are not involved. So actually, I just assume them. I just keep what was operationally used, which is a statistical approach about the correlations, and then applying Gaspari cone functions to ensure localization. So I didn't change this at all, and I'm not propagating the error correlations. I would definitely like to do this. I think it's very important. It has been done in theoretic and more idealized studies. So I'm just looking at the literature I'm having here. But I'm in some of the work from Olivier Pencook. I think he pretty sure he uses the error correlation length. Maybe even in all of them. I would have to look up. But yeah, and to the related question, how I would like to implement this, there has been work on deriving the equations for the error correlation length as well. They get much more complicated, but there are also, you can apply leading order approximations to this. So I would probably try to go with this to have a simplified propagation, which is still better, of course, than the simple assumption that I have right now.
Got it. Is it accurate to say that currently you're incorporating correlations through localized ensemble representation, whereas the standard deviations are being analytically propagated through the dynamics. Is that a correct understanding?
Almost, yes. So we're not having an ensemble in air quality. That's one of the reasons why we're using the parametric approach, because in the operational setup, we can't afford a reasonable ensemble size. But for the correlations, it's basically based on an offline ensemble approach.